Glenn is a professor at the University of Missouri, Columbia. Before joining the university, Dr. Washer was with the Federal Highway Administration at the Turner Fairbank Research Center, where he served as the director of the FHWA Non-Destructive Evaluation Program. He has conducted research for state DOTs and NCHRP throughout the 25 years of experience, developing new technologies for the non-destructive evaluation and inspection of highway bridges. Please welcome Dr. Glenn.
How do I find myself here, Claude? All right, well, good morning. As Claude said, I'm Glenn Washer from the University of Missouri. Make a presentation today about thermal imaging, and this is the objectives here to, in part, provide an update on a pooled fund that many of the states that participating here were participants in, that occurred over a number of years. So I think it started all the way back in 2007 and finished up in 2015. And also introduced some new infrared technologies that were developed in part through that pooled fund effort. And so this is the states that were part of that pooled fund. And that pooled fund had a couple of parts. The first part was an experimental part that looked at the weather conditions that were suitable for infrared thermography, you know, because infrared thermography works by the temperature difference between a defective piece of concrete, typically something that's got a delamination, and an intact portion of the concrete. And that depends on the ambient weather conditions changing in order to create a gradient in the concrete and produce that temperature difference. And so we had a project originally that looked at what were the environmental conditions that were suitable. And in that project, we did a lot of things like we built a big concrete block in the field in Missouri, and we stared at it with an infrared camera for 3 months on the side that was getting hit by the sun and 3 months on the side that wasn't, and developed a lot of data like this here. And so this is what this figure shows is the top blue line is the ambient temperature changes over 2 days, and they sort of go with this right axis here. And down here is the thermal contrast, that is the difference between the temperature of on the surface of concrete that's intact as compared with the surface above concrete that's got in this case, a styrofoam target embedded in it at a depth of 1, 2, or 3 inches. And so when you look at a thermal image, a typical traditional thermal image, and you see color differences, those color differences are the thermal contrast. So if you had a picture that was mostly blue, this thermal contrast here might show up as red. And so what we show in this diagram is delaminations that are 1, 2, and 3 inches deep in the concrete, and how that thermal contrast, that is that appearance in the thermal image, varies over a course of 2 days. And that goes with this axis over here on the left. And so the things that you notice about it are that, well, a deeper defect doesn't create as much thermal contrast as a shallow defect. That's the first thing. Also, that contrast develops later in the day. This is 2 days along the horizontal axis in time here. That develops at a different part in the day. So if you were, for example, looking for a deeper delamination, you might go later in the day. A shallow delamination might be more apparent early in the day. In this case, these data are for an area that was never exposed to sun. So this is just the ambient temperature effects, okay, of something that's in the shade. The other thing you notice is that twice a day there is no thermal contrast between your defect and the intact concrete. And so if you do an inspection at that time, you'll never see them. And so you have to avoid those times, right? And that takes some knowledge, and it's not that difficult, but we produced a guideline that said, you know, do it between these hours and those hours using a conventional infrared camera, and those are available on the website, those guidelines. And there's also a web page you can go to on your cell phone when you're at a bridge, and it will locate your position and tell you whether you're in these good time windows or not. And that continues to be available for free to people. The other thing that we did during the second phase of that pooled fund was we trained state DOTs and gave them infrared cameras so they could use it within their own programs to see how that worked. And along the way, we explored a couple of new technologies, because there was some new technologies being developed under an SBIR with Federal Highways that was a compact thermal imaging device that was originally being designed for coatings. And that's SBIR continues now, looking at infrared analysis of coatings to find corrosion underneath coatings. We took that technology and we made it into 2 different systems that were configured for inspection of concrete. One was the DSS, and this stands for a deck and soffit scanner. It's a mobile system that operates around 5 to 10 miles an hour, and it's more like a traditional infrared system if you did an infrared scan of a deck. This is similar to that, with the difference being that it's focused more on doing high resolution imaging. And an IRUTD, which stands for ultra time domain, That's a new tool for condition assessment. We hadn't had something like this before. And the general idea is that it captures images over time. So you position a camera above a bridge deck and you collect data, say, for 24 hours. And then you have information from both heating and cooling cycles. So when you look back at our previous graph, you see that, during the day this got hotter, but during the night it got cooler. And so if you capture the full 24 hours of that, then you can increase the signal-to-noise ratio and get better data. And this overcomes some limitations of conventional handheld IR. It can give you some information about the depth of the damage. It's not as dependent on the weather, and it's very reproducible and quantitative. And so I'll show some examples of that. This is the DSS system, and I brought just some examples that illustrate the kind of images that are produced. This is the imaging camera head up here, and this is a regular visual camera and an infrared imager. And it travels down the road and it fires the camera based on an encoder wheel. And as I mentioned, this is designed to go around 5 or 10 miles an hour, so you do it with moving traffic control. Those are then stitched together, so you see, for example, this is a 1-lane wide section of bridge deck. Here's the visual image here, and here's the infrared image there. This is what a 150-foot long deck looks like. Okay, so you see that it took 4 runs to cover the whole deck. Those are then stitched together, and this is a visual image here, and then the infrared image down here. And one of the things that's unique about this system, we think, is relative to others, is produce very high resolution data. And we saw some interesting things in this particular bridge when we looked at the results and looked back historically at some Google Earth images that have been produced for the bridge deck. So down here you see, this is a sort of a long bridge compressed onto a small piece of paper, but the data is very high resolution. So if you blow it up, you see data like this. And what you see in this visual image is there's a patch here, and there's a crack that's been sealed here. And here's the infrared image of that. What you see, I'll show a little larger blow up here on the next page. Here's the crack that's been filled. At some previous time, someone came through and did an asphaltic filler on that crack. And we look back in Google Earth, and this had been done about 5 or 6 years earlier. What you notice is that repair there was effective. There's no delamination in the area of that crack, and so that was successful. Even though there's a lot of delaminations in this bridge deck, that seal was effective in protecting that area. Nearby, this patch here, right, it's got delaminations which are growing off it. And so you can kind of see a little bit of a sense of that these are different images that have been stitched together, but you see the resolution around that patch. You can see areas that are growing off that patch that are delaminations now. And so that's an area where that patch either needed to be larger originally, or it's this effect of when you install a patch, you get some corrosion nearby to it. Now that's a conventional infrared system in that you go out at a particular time of day. Hopefully you're there at the right time in the afternoon or midday to afternoon, and you're looking for the areas where there's thermal contrast between defective area concrete that is a delamination typically. And this infrared detects basically the thing a hammer sounding will detect. There's a delamination there that interrupts the heat flow, and so it's very comparable to that. A UTD is a different concept altogether, that you're going to take an infrared camera and mount it in a fixed position on a bridge deck and image a portion of the bridge deck over a 24-hour period. You can do it for less, as little as 4 hours sometimes, but essentially collect data over a period of time. You collect lots of these images, and then they're processed. And they're not, what's produced out of this is not a thermal image in the conventional sense that you would think of it, where these colors in the image represent temperature. In this case, the colors in the image represent thermal inertia. There's a rate of change of temperature over 24 hours. And so I'll show some results here that illustrate what you can do with that. It gives it some unique properties. How do you mount it? Well, you mount it on either a light pole or a sign structure. We have a pneumatic mast you can put on a bridge and launch up above 30 feet above the bridge deck. There's vehicle mounted masts. We've done them on light plants that are, just take the lights off and put the camera up there and look at it up above the bridge. Here's one on a sign structure on a bridge. So that you position it somehow above the bridge, and 25 to 30 feet would be ideal. It shows a visual picture of the bridge, which is shown here. So this is a bridge that we did in Iowa. This is actually one of the first field tests we ever did with the technology. And what you see here is we've placed some markers on the deck just for research purposes, and these are steel tape essentially. So they always show up a different color because they're a different material altogether. And then Iowa DOT was doing some epoxy injection on this deck at the time that we were doing thermal imaging. Remains open to traffic. Now, this wasn't a really heavily traveled route, but the bridge does remain open to traffic because really the cars are not there for that long. If you're collecting data, a lot of data all the time, you can process out that data. But here you see this is a conventional infrared image. He's got a little bucket of kimchi or something in the back of the trailer there. And so there wasn't a lot of traffic, but you see this is open. This is during a period of time when it was open. It was closed during the day because they were doing, one lane was closed. They were doing epoxy injection activities, okay? So this is what the UTD image looks like. It shows the areas of delamination here. Deep areas show up as one color. They have a different rate of change than shallow areas. Shallow areas show up as a different color. You see about 3,000 square feet of bridge deck in this particular image. In this case, we had a fixed camera. Later, we put a pan and tilt on it so you can do 3,000 feet in either direction, really, or probably even more if you get a little higher. We compared that with hammer sounding done by Iowa DOT folks that were out there doing the epoxy injection. We asked them to paint around their circles in orange so we could take a picture of it with our camera that's mounted up on the mast. And you see an overlay here that shows you a comparison between the detailed hammer sounding and our infrared results. Now, these images were produced pretty quickly. It's one point to make about these is that they're, if you look at this data, you know, this is all data. This is not a processed image that's been line fit and curve fit and everything else. These are all data, and this is a 640 by 480 image. So that's how many pixels there are there, and that's the data value from the pixels. This is data that was collected after one of the lanes had been epoxy injected. So this is before the injection, this is after the injection, so you can sort of see the effect of that. There is some little dark spots there and where the epoxy is in the shallow delaminations. I don't know if that's an effect of the epoxy curing or anything. This was done all in a 1 week period, but generally you can see that the thermal contrast that you're getting up here is not present in this lane that's been epoxy injected. A couple other examples of this technology. Here's a cast-in-place box girder, this is another one of the early tests, and we tested this just to illustrate how reproducible this might be. This particular bridge was built, I think, in 59 or 60. It was never open to traffic, so the approach spans were never built. So it's just been sitting there for all this time, and you see this grass growing at the end of it. It's kind of like a, you know, end of the world scenario or something. So we were able to test that. Here's defects that were located in it. You can also see the webs of the cast-in-place box and the diaphragms through the deck. MoDOT chain dragged that for us. Here's a comparison between, you know, their results and our results, and so those very consistent with a chain drag result. Because this bridge is closed, we were able to test it over different periods of time. So we did tests that took over different time intervals. For example, you know, this is 6 hours. This is more like 12 or 11 hours. This one's more like 12 and a half hours on different dates. So this was done in 2014 in June. This is in August of 2014. This is in September of 2015. And what you notice is even though the weather conditions are different, the approach angle we're taking, we're at different positions on the bridge deck. You can see that the camera's looking from different angles. The defects are reproduced in each of the images. It's a very reproducible method this way. It's not it's more tolerant of environmental conditions. We've also done some testing on voided slab bridges. For example, here's you're looking up at the bottom of now gone, what's now, this bridge is no longer there, but the underside of a voided slab here. And this data is collected over just a part of a day, maybe 4 or 5 hours. And you see the area here in that voided slab that is saturated with concrete, that's saturated with moisture. And then you see where the intact voids are. Those show up as an imprint in that image. And again, this isn't a thermal image, this is a thermal inertial image that is collected, in this case, from data collected over 4 or 5 hours. Here's another example of a voided slab. This is right in downtown Columbia. The roadway underneath here is Route 63, which is a state north-south route that's pretty busy. This is a picture of what the bridge deck looked like. So this is a very challenging situation for any infrared system because the surface is very inconsistent. There's a sort of a epoxy or asphalt overlay, thin asphalt overlay, but it's not consistent. It's worn out or worn thin on certain parts of the deck, and there's holes in it. There's also a large number of patches. This is a visual image here, okay? In this case, data was collected from a position behind the parapet at the end of the bridge using a light plant. The camera's launched on a light plant up above, 25 feet above the bridge deck, but it's behind the parapet. We never went on the bridge or touched the bridge to get the data. This is a very active route. This picture's taken at like 5 in the morning when there just happened to be no cars on it, but there's almost always vehicles on this bridge, turning to the north and south, turning north-south to Route 63. This picture down here, which I'll show a little better later, is a image of the structural configuration of the bridge. That is where the voids are in the diaphragms. This is the processed IR data that shows thermal inertia results, that shows delaminations in the surface of the bridge deck, and this is an overlay of those two. And this is one of the unique characteristics of this technology, that you can image the internal features of a bridge and get some interesting results. And so this is not as clear on your screen as mine, unfortunately, but what you see is that you can see all the voids in this bridge. You see the horizontal diaphragms. Here is the support, right, the thick diaphragm over a support, and here's a thick diaphragm over the second support. And what you notice in the image is this is processed, time data that's processed to highlight the internal features of the bridge and the patches, and you notice that almost the vast majority of patches are in the negative moment region over the supports, which is kind of an interesting thing that you might not notice otherwise. And so you can see all the features of the bridge, and by processing the data differently, see what the delaminations look like in the surface of the bridge. How do these two technologies compare? Well, here's some images taken off of a bridge deck. This is a bridge deck that's about almost 2 miles long. It was scanned with a regular sort of conventional IR using the scanning system, and so you see here, here's a delamination. This is a core that was taken that shows it was a delamination. This is a patch. This is a conventional IR image. This is a UTD image that was taken by mounting the camera on a light pole nearby and scanning this area, and this is cut down to just show the area of the defect here. So you see in those two, they're pretty consistent between the two. This is a thermal inertia picture. This is a thermal picture. In another location on the same bridge, here's a defect that was located with, in the UTD data. Again, this is the thermal inertia data on top. On the bottom is the conventional IR data. And there's shadows in this data. This is from a sign structure here, this small shadow on this deck. And what it produces, it fails to produce a thermal contrast in the area where the delamination is in that case, because there's a shadow moving across it during the day. And so you have an advantage of having collected data over 24 hours to have seen that without shadows and eliminate. You notice in this image there aren't any shadows, because those are, although they move across the bridge and they get processed out in the data processing. Okay, so what we showed here was a couple of technologies that, again, they were developed through this pooled fund. The IR DSS is a high-resolution, more conventional IR system. It can be flipped up to do the soffit area of a bridge or a bridge deck. It's configured so it goes on any truck with a tow hitch on it. And we showed some examples of preservation needs of results with that. And the IR UTD, which is a new technology for thermal imaging, it's a transient thermography technology, and so you mount a camera in a fixed position above a bridge deck and collect data over a set period of time. It's quantitative and more reproducible. You can determine depths, at least qualitatively. We don't have that quantitatively yet, but that's a matter of processing in time, I think. Doesn't require traffic control on the deck while you collect data, and it can be used for a variety of things, deck, soffits, substructures. We've done columns. We've done a number of other features. It doesn't require to be out in the sun, for example. It can be the underside of the bridge deck and other things. We've been working on commercializing the research results from this. As I mentioned before, it originally came out of an SBIR. So we put together a company it's called ThermalStare that offers this as a commercial business. Currently, we're doing some work with several transportation authorities, toll road owners, and also with the U.S. Navy on application for ships, which has been very interesting. So. All right, and I'll be happy to answer any questions if anyone has any. Thanks. Yes, sir.
So can you do this year-round? You talked about putting it out there for the day or whatever. Can you do it all year round?
Well, yes, no, and maybe. I mean, you know, how year-round do you mean? In really severe cold weather? I mean, I guess you could do it. I think if there's
no,
a
I just mean more than spring or fall.
Yes,
Okay,
you can do it
all summer.
Yeah, I mean, in the minus 20-degree weather probably is not very good. You know, when there's snow on the deck or there's potentially ice captured in the areas. But I'd say the season, you know, depending on where you were, the non-frozen season is when you'd want to do it. When it's freezing temperatures, you know, you can have complications. Not necessarily impossible, but like in Missouri, we have a lot of freeze-thaw. You know, we go the long periods of the year when it's frozen at night, but not in the day, and that's fine. It works in that period. But, you know, real cold, I don't know. Yeah.
Any other questions?
So if a state wanted to do this, how does it work? Can you buy the equipment, or do you have to hire the service?
Yeah, well, we're using it as a service currently. The technology, the equipment and hardware was originally developed in SBIR and then further developed a little bit under the pooled fund. And so those are kind of unique instruments that we make. And right now, we're offering that as a service that you hire, yeah.
Just a quick one. Now, you're looking at delaminations, but at kind of a smaller, closer frame of view. Do you think it's possible you could use this technology to help locate reinforcing steel, for retrofits if we're going to put anchors in or something like that?
It's possible the UTD might be used in that way. We've not tried to do that. You do sometimes see in even conventional IR, because the thermal properties of the steel are different, sometimes you'll see reinforcing steel patterns show up. And so, that tells me that it's possible to do it. We've never been asked to do that or tried to do that. I think that there is, something like GPR magnetometers do it fairly readily, so we've not looked at that as an application for it, so.
So is that mainly applicable for cementatious deck at the top, asphalt membrane, you don't see through something?
Well, asphalt is, again, it depends on what you mean by asphalt, but, if it's 6 inches of asphalt, the stuff's likely to be, diminished. If it's, 2 or 3 inch course of asphalt and you're using the UTD technology that looks over time, then you have a good chance, that's going to work for you. Because it's layered structure, but the whole structure is changing temperature. As you get into 2 and 3 inch range with conventional IR, it's very challenging. You don't see the same contrast that you do. Contrasts are smaller. But one of the advantages of collecting data over 24 hours is that whole structure's changing temperature all the time, and you're not looking at now the temperature change that manifests on the surface, but the time rate of change of that. And so, I think it's more effective in that situation. So we've done really modestly thin ones at this point. So, but I'm pretty confident it'll work well in the 1 to 2 inch range. So.
Great, thank you.
All right, thank you.